Hello, we are Group 66 from Distributed Systems. For our Distributed Systems final project, we built a high-throughput computing cluster on AWS to perform pet biometric identification. In this diagram, it shows that our architecture consists of 5 nodes: the central manager, the condo master, a submission host, 2 worker nodes for parallel processing, the execution host 01 and execution host 02, and a centralized NFS file server for shared storage. First, I am going to go into the submission host's terminal. I'll navigate to our project directory, pet_project, which is located inside the MNT shared folder. This is crucial because this folder is mounted from our NFS server, allowing all nodes to access these files. Then let's go to the condo master. In here, we can check the live system. Here we can query the central manager. You can see that we have 2 execution slots available, the execution host 01 and 02. They are currently unclaimed because the system is idle. And for the IP, we can check the execution host 01 private IP ends with 31.151, and it shows here. And for the execution host 02, the private IP ends with 17.75, and it shows here. Going back to the submission host, we can check our output folder. Our output folder is currently empty, and we are about to process a batch of 50 images. This is our condo submit file. We have configured it to queue 50 parallel jobs. Each job runs a Python script that simulates AI image classification. Now we are going to submit the workload to the cluster. You can see 50 jobs over here have been submitted to the scheduler. Now we can run condo_queue to check the queue. Checking the queue, we can see the jobs listed here. Some are waiting and some are already being assigned to workers. So it shows that there are 46 jobs currently. 4 are done, that's why it only shows 46 jobs. And out of the 46 jobs, 42 are in idle and 4 are currently running. And let's take a look at the status. We can run Condor status. The slots have been changed to claim and busy over here, and the master is actively balancing the load across our 2 worker nodes, the execution host 01 and 02. And as soon as a worker finishes one image, it grabs the next one instantly. Now let's check again with the condo queue. Now it shows that 24 jobs are done, 4 are currently running, and 22 are in idle. So there are 26 jobs left. Now let's inspect a completed result. No, So here is a completed result. Notice the process by field. This proves that this specific task was executed on the execution host 02, and the result was saved back to our NFS shared file. Now let's check back how many jobs are there left. There are currently 6 jobs left. So while the jobs are running, this is our instances of the architecture on the AWS. We have the file server, control master, submission host, and the two worker nodes, the execution host 01 and 02. Now let's check back. So it shows that everything is done, then 0 jobs left. So now that all 50 jobs are done, we can run our aggregation script. Let's take a look at this final report as it provides the proof that our distributed architecture is working as intended. First, look at the process by column. If you look closely at the first few rows, you will see the IP addresses alternating. This demonstrates that the htcondo scheduler was actively performing round-robin load balancing. It didn't just dump all jobs onto one machine, it intelligently assigned tasks to whichever execution slot became free first. Second, notice the data aggregation. In a real-world scenario, these jobs would finish at slightly different times. However, our merge system has successfully collected these asynchronous results from the shared NFS storage and resequenced them. Our final output is a clean, sorted list from image ID 0 to 49, proving we maintain data integrity throughout the workflow. Finally, regarding the scalability, we process 50 images here, but because this architecture is horizontally scalable, we could easily increase this to 5,000 images simply by launching more EC2 instances without changing any of the code. This successful test confirms that our platform meets the requirements for high throughput distributed data processing, and that is all for our demonstration of our project. Thank you very much.